worksheet? We left off yesterday in nomenclature with these degrees of substitution. So could someone reiterate what a degree of substitution is, or what we mean by that? How many carbons is something bonded to? So it's a regiochemistry label, and we use it to describe these carbon by carbon specifically. So what degree of substitution is lacking from this molecule? What degree of substitution is not present in this molecule? Tertiary. There's no tertiary carbon. A quaternary carbon, 4 different primary carbons, and a secondary carbon, but no tertiary carbon. I think you could argue also there's no methyl carbons. There are methyl groups. There are CH3 groups, but all of those methyl groups are primary carbons. There's no carbon that's bonded to no other carbons. There's no methyl carbons. Okay, what about when I make this modification? Could you describe the functional group in this molecule, not just naming the functional group, but describing the substitution of the functional group?
Alkyl halide.
Alkyl halide.
And it's sorry, what was the second part of that question?
How can you use degrees of substitution in describing the functional group?
Oh, it's
Tell us where the
like what prime
halogen is.
Right, like tell me what type of carbon the halogen is bonded to.
Which degree carbon?
Go 1 degree.
Is it a primary alkyl halide?
Yes.
I disagree.
Quaternary.
Not quite.
Dang it.
Tertiary.
Oh, because of that little.
I swapped out a methyl, so now there is no longer a quaternary carbon. It's now bonded to a tertiary carbon. So this is a tertiary alkyl halide. How about comparing these two functional groups?
An alkane and alcohol. Yeah.
We'll skip alkane, and we'll say we have an alcohol in both structures. How can I describe the substitution of the alcohols as well? Or describe more about what substitution they're bonded to? Secondary alcohol? Primary alcohol.
Only one.
The oxygen doesn't change the substitution of the carbon. The carbon is bonded to one other carbon. So the alcohol is part of a primary carbon, so it's a primary alcohol.
So with something like an epoxide, where
Yeah.
it has the carbons going across, connecting to each other and the oxygen,
Yeah.
would the carbons on either end of those be referred to as tertiary? Like the one you specifically drew with the...
This is a primary carbon,
Yes.
and that's a tertiary carbon,
Yes.
because bonds to hetero-atoms don't change the substitution. The only thing that we describe are bonds to carbon. And so it would be harder with an epoxide. You can't say it's a primary epoxide or a secondary epoxide because there are 2 carbons to consider. What about the other alcohol?
Primary as well?
No, because primary tells us the carbon is attached to one other carbon. This is a methyl alcohol. In fact, sorry?
What's the other alcohol? CH3? Is that what you're just saying?
CH3OH.
Are those two? That's just one alcohol.
Yes, methyl alcohol and primary alcohol.
Oh, the same thing.
I'm so confused.
Wait, no, these are two different molecules.
I'm just.
Oh,
Yeah.
okay.
Do they look connected?
No, I just,
They thought that you were spelling out the structure.
The primary
Which
alcohol
I was
and
confused about.
for the-
because I was
no, I
like,
thought you were
Yeah.
asking about the
They
other
thought that
alcohol on the.
your drawing of the primary alcohol, that was just the name of it. They thought that.
This is its substitution. This is a methyl alcohol. Because the carbon of the alcohol is a methyl carbon, it's not a primary carbon. This is not a methyl alcohol, this is a primary alcohol. Are we on the same page?
We're on the same page.
Elvira doesn't look like it. Delaney looks like it.
I don't know, I don't know where I am.
Here's one alcohol molecule.
Yes.
Right.
It's not a secondary alcohol, it's not a tertiary alcohol, it's a primary alcohol. Here's a different molecule.
It's different, that's, yeah, never mind.
Can I just ask though, why was that not obvious? That they're different?
Because when you said, where's the other alcohol, I thought you were talking about the one primary one, and I was like, there's only one, how could there be another?
I
You
see.
were talking
I
about
think
the-
I misspoke if I said where is the other? I think I meant what about the other alcohol?
That's
Okay.
Okay.
All right.
Sorry.
Great. Now, it is also its name, and that was the segue that I wanted to use for it. This name, methyl alcohol, is an example of functional class nomenclature. In functional class nomenclature, we name the carbon chain as a substituent of the functional group. So we have methyl alcohol, but IUPAC nomenclature would, a systematic nomenclature would instead have the root and the suffix and the stoppers. This has a functional class name. We can call this N-propyl alcohol, or we can call it N-propanol. So there are different types of nomenclature. We're not going to go through functional class, but in my opinion, when you see a functional class name, it makes a lot of sense. We're going to be going through just IUPAC nomenclature, the systematic nomenclature instead. Okay, so we had introduced degrees of substitutions, and because of that, we had introduced these two substituents, these two groups that are fairly common, and we said that this group is a sec-butyl group. So for instance, if it's connected to an alcohol, we call it sec-butyl alcohol. We said that this group was a tert-butyl group because of its tertiary attachment. So we can call this compound tert-butyl bromide. And again, this is just kind of emphasizing how degrees of substitution shows up inside of nomenclature. Here's a secondary alcohol on a 4-carbon chain, sec-butyl. Here's a tertiary alkyl halide with this 4-carbon group, tert-butyl. The issue is that when these groups then become part of the parent chain, or substituents off of a parent chain, we still look at them and refer to it as a sec-butyl group. But would you agree it's no longer actually a secondary carbon? It's now a tertiary carbon. But it as a group would have come from a secondary carbon. Or with our tert-butyl, when that tert-butyl is actually a substituent of a parent chain, would you agree that that is technically a quaternary carbon, not a tertiary carbon, but it's derived from this name as if it were a tertiary carbon? I mean, it's okay to hate it here, but it makes sense in a way if you approach it from the right direction. Okay, so our sec-butyl group is a tertiary carbon, our tert-butyl group is a quaternary carbon, depending on the context.
So, like for a rule of thumb, when we're drawing these like substituents and naming them, would it be good
Yeah, that's not bad. Or you might just get familiar with their shapes. And when you see that squiggle, you know it's sec-butyl. When you see that chicken foot, you know it's tert-butyl. Because in the example that I give you a molecule like this, and I ask you, how many methyl carbons? How many secondary carbons? How many tertiary and quaternary carbons? I don't want you to say that the tert-butyl group has a tertiary carbon. Because in this molecule, the tert-butyl group doesn't have a tertiary carbon. The tert-butyl group has that quaternary carbon.
Okay. So when you're counting carbons and what degree they are, you see the molecule as a whole, but when you're naming branches, you don't.
When you're naming, don't look at the actual degree of substitution. When you're assigning degrees of substitution, look at the molecule, don't think about the groups. Yeah, close one eye to look right and close the other eye to look the other way. All right. So I want to talk about the next most important part of the name. We talked about the root and how they give us these descriptions of the carbon chain, which is how we got to this in general. These descriptions of the carbon chain are kind of unique, and so I wanted to take that deviation to degrees of substitution. But now I want to get us back on to the suffix, the locant that's needed for the suffix, and sometimes how the suffix is stoppered. Oh, I guess I didn't put locant in there, did I? Sorry. Suffix, the suffix stopper, and the multipliers. But I guess, yeah, we'll come back to the locants later. Now, the suffix tells us about the major hydrocarbon functional groups. If the only hydrocarbon functional group in the molecule is an alkane, then we give that suffix -ane. For example, when we burn natural gas, we're burning methane. The only functional group there is alkane. Same with butane, propane. If there is an alkene in the structure, then we add the suffix -ene. So if I have a 3-carbon chain and I have an alkene, I give it that root prop and the suffix -ene. Then we can have -ine for alkynes, but there is also a way to indicate that a parent chain has both alkene and alkyne. Both of those groups end up in the suffix. So you remember yesterday when I said some people don't consider alkane a functional group? Which is why if something more than alkane is in the molecule, alkane just gets dropped. But if both alkene and alkyne are in the molecule, I can't drop either one of them. The only way that alkenes and alkynes show up is in the suffix. The only way I know those hydrocarbon groups are in there is because of the suffix. So I can combine them, and I can have a suffix that tells me I have both an alkene and an alkyne. Now, the stoppers, I do believe that this is something that I invented, so I'm not sure that you'll see this in any textbook. Modify the suffix for one other functional group. Which group that is based on the order of priority. Carboxylic acid is the highest priority, and then esters and amides and ketones and aldehydes and alcohols. But in our class, the only functional group that we'll be learning how to name are alcohols. Those are the one group that show up in the suffix. Now, when I say that they modify the suffix for one group, I mean you cannot modify the suffix to share that both an alcohol and a carboxylic acid are in the structure. Either the alcohol gets to modify the suffix or the carboxylic acid gets to modify the suffix. But otherwise, the group has, if it can't go in the suffix, then the group has to get a substituent name. Shows up in the prefix. For our class though, alcohols are the only thing that we'll learn to modify the suffix. So this can take, we give OL for an alcohol, and the way that this looks is alkane drops the E, and it's modified to enol, like when we have ethanol. Ethanol. Notice how the suffix is still informed by the hydrocarbon chain. It's not informed by just the alcohol. This is why I don't like to say that the alcohol is a suffix. The alcohol doesn't give a suffix. The alcohol modifies a suffix from the hydrocarbon, because ethyl is not how we communicate a two-carbon chain with an alcohol. Ethyl leaves off the ane. Okay, in the same way, we can get ene to drop the E and become enol. Although you will more often see this with, you know what, I'm going to give you a few different renderings of this. You might see this dash before and or after the two parts that are now the suffix and the suffix stopper. Ein becomes einol. But we can take ein and we can make einol. Old MacDonald had a farm. Einol.
And so that would be if it has alkenes and alkynes
And alcohols.
and alcohols, right?
Yep.
And could it also have alkanes, but we just don't talk about it because
Yes. Well, that we don't talk about it because who agrees on the definition of alkane? I feel like I disagree with most people, actually. I think everybody else agrees except for me. For instance, if you have an alkane, because it's sp3 carbons, only bonded to carbon and hydrogens, but it's bonded to an alkene carbon, then it's not really alkane, it's allylic. And allylic has different properties and different chemistry than alkane. If it's bonded to an aromatic ring, it's not just alkane, it's benzylic. So there's kind of, like, depending on what else is in the structure, it does change. There is a hydrocarbon I'm not giving you. We're not talking about the aromatic rings. Once we get into OChem 2, we learn the nomenclature for benzene and its derivatives. So we're focused on alkane, alkene, alkynes, enenes, and how they get changed up with our suffixes, our suffix stopper. All right, so I want you to notice the A comes from that suffix for an alkane. We don't have that A anytime there's something of higher priority. And we drop that E anytime we modify the suffix with a suffix stopper. Until we introduce multipliers, if I have multiple of the same functional group in my structure, I need to communicate in the name that that functional group appears multiple times. So the multipliers tell us the redundancies of a group. Obviously, we do not use a multiplier if the group is there once, because we already have to communicate that, so we're not going to put mono in front. We're not going to say monofluoro. We're not going to say monomethyl. We're not going to say monoene or monool. But if we have 2 redundancies, we'll use di. If we have 3 redundancies, tri. 4, I wonder what you guys think. What multiplier can we use to communicate 4? Rowan? Quad? Liana? You're thinking quad as well? Any others? What else do we know communicates 4? Tetra or quart. What others? There's a lot, right? We're going to use tetra. And then from there, it's everything that you're used to. Penta, hexa, hepta, octa. I don't think you'll see beyond hexa in my class. I'm not sure that you'll see tetra very often either. Okay, so we have these multipliers, and they need to go with the substituent, or with the suffix, or with the stopper to describe that that group being represented in the suffix or in the stopper is there multiple times. But we're taking suffixes that start with vowels and stoppers that start with vowels, and we're combining them now with multipliers that start with consonants. Did you know this was going to be a language class? Like actually a language class. In IUPAC nomenclature, they don't want to butt up vowels to vowels, and they don't want to butt up consonants to consonants. That's one of the reasons we dropped the E and then placed the OL so that we didn't have EOL. We didn't want vowel to vowel butting up, so we dropped the E. Okay, so now if I have something like an alkane and I have a diol, before I would have dropped the E and I would have combined ane and ol. But now I don't drop the E and I keep it as ane diol. I'm going to draw that in a little bit of a different spot. And I'm going to put in a dash there between them. And I'll give you an example. Before I had methanol, before I had ethanol, we could have just as easily seen methanol. Okay, I'll just write out the whole example. Methanol, CH3OH. Methane diol. The E comes back. It's like I stoppered ane, but now to stopper with diol, I just leave ane exactly as it is. There's still a suffix that indicates hydrocarbon functionality. Ane is still present. But I don't drop the E anymore, and that's so that I have the vowel to consonant lineup. If I had dropped the E, I would have had consonant, consonant, N and D butting up next to each other. Methanol, methane diol. Gavin?
Where's the diol from again?
Well, it's saying that there are 2 alcohols.
Okay.
If I have 2 alcohols, I can't just say all. I need to clarify that there are 2 of them. We are clarifying the redundancy, the repetitiveness.
The methane, is that one alkane?
It's a 1 carbon chain. Methanol, 1 carbon chain with an alcohol. Methane diol, 1 carbon chain with 2 alcohols. And I know that looks like a weird structure. If you wanted to see that structure drawn out as a bond line chain, not like it communicates a lot more effectively what it is, because that carbon is assumed and it looks a little bit silly. Let's look at how this happens with some of our other groups. Well, first of all, because no one really believes that alkane is a functional group, we don't have diane, triane, tetraane. But alkenes and alkynes are functional groups, so we can have diene and diine. If I take a structure that has a 2-carbon chain and 2 alkenes. No, I'm sorry. That literally doesn't work. I meant a 4-carbon chain. Can't have 2 alkenes and just 2 carbons. A 4-carbon chain and 2 alkenes. The root that I get for a 4-carbon parent chain? No. No. Bute. Yep. I know, it's crazy, right? Bute. The suffix I give for an alkene? Ene. The multiplier I add for 2 alkenes? Di. So this is, sorry, I'm going to put this above it. This is bute, and this is diene. I don't want that T and D butting up next to each other. So we call it butadiene. Where did that A come from? Huh? It's an article?
I want to say this came from the ane.
It feels like it came from the A of ane. It feels like we took butane and then dropped off the N and E. Because the root is not buta. The root is bute. So where did that A come from? It is just a figment of IUPAC nomenclature to give your mouth that space to put consonants further apart. Instead of butadiene, we call it butadiene. Lovely. It's a little crazy, and that's okay to say it's crazy. Somebody said, you said something?
I just said a little arbitrary.
Yes, and so I will say, for the most part, if I'm grading nomenclature, and you're like just missing on these weird little parts, I'm not such a strict grader on the weird grammar rules. I'm looking to see that you've got the parent chain correct, the suffix correct, the multipliers correct, the locants correct. You added an E where you shouldn't, you forgot an A where you should have. It's okay. I'll get over it. Okay.
Is it always an A or is it sometimes like an E or not?
That's a good question. It's always an A. If you've got diene, triene, tetraene, it's always an A that comes with the root. So I would still look at this as the root now is buta. The A comes with the root, not the suffix.
So would you end up with tetrene?
You could have tetraene.
Okay, you wouldn't end up with a bunch of weird A's, you would just drop the A and substitute the ene.
Okay, well, let me give you an example. 8-membered ring, cyclooctatetraene.
You don't drop the A?
No, the A comes with because of tetra. It should be octene, cyclooctene, or cyclooctetraene. But we put the A in because there's a multiplier for the suffix.
Why is it not tetrene?
Yeah, we can call them if you want and ask.
You're asking, right, 'cause you said we don't want vowels next to each other.
Yeah, so
I know, and I've got cyclooct with 2 O's next to each other, which think of monoxide, carbon monoxide, doesn't have 2 O's next to each other. IUPAC dropped those. So I don't know why they don't call it cyclooctane. They call it cyclooctane, cycloctane. Cycloctane does sound a little crazy. And we do keep the A and the E from tetraene. I know. Listen, I would say most of the rules come from what feels best in the mouth.
But tetraene does not feel good.
Cyclooctatetraene. To me it does. Cycloctetrine.
No, better than, no, cyclooct, I'm with that, the cyclooct, but why is it not tetraene? Why is it, like, that doesn't make sense.
I know. I'm not sure that they cared that it made sense.
Tetraene sounds bad.
Tetrine. Tetrine kind of sounds like latrine, like a toilet. All right, how do you guys feel about your suffixes? This is really all I wanted to talk about with suffixes. We're going to apply them as we keep going, but those are your suffixes.
I was gonna say, like, can we go through some of these examples here and see?
Oh, you want to do the molecules that I put down there on purpose for us to name? Yes. Thank you, Michael. Thank you for the reminder. All right, so first molecule, can you find the longest carbon chain that contains the highest priority functional group? Can we review what are the highest priority functional groups for this semester, not of all time? Alkene is tied with alkyne. And then alkyl and halogens. Okay, so the highest priority functional group?
Right there, it's the
Alkene. Okay, there's actually a lot that goes into getting the full name for this, so we can come back at the end of this worksheet and give the full name. What I want to focus on right now is root and suffix. So anything that's a substituent, we're just going to ignore for now. We're just going to name the root and the suffix. What is the longest parent chain that contains the highest priority functional group? Looks like 5 to me. Do you notice how the 6-carbon chain along the bottom does not include the alkene? It touches one of the carbons of the alkene, but it doesn't touch the alkene. So I either can start from the alkene and go to the right, or from the alkene and go to the left, and that looks like a 5-carbon chain. So the root and suffix together, pentene. And again, we can come back and figure out how do we describe where the alkene is in the chain, and how do we describe the rest of the carbons in this molecule. So we'll talk about that more.
Sorry, just to clarify the rules again. So you started up there in the alkene because it's the highest priority group.
Yep. It's the highest priority present. And so I'm gonna make sure I have the longest carbon chain for the highest priority group. What about this next one? Evelyn?
Yeah, it's a 4, so it would be, butene.
But it won't be butene because now I have 2 alkenes. Butadiene. See that? You see how I went to a shorter carbon chain than even before? Still not the longest possible. Still not even the longest possible for one alkene. But I'm not prioritizing just one alkene, am I? I'm prioritizing alkenes. So I want the longest carbon chain that contains both of the alkenes, even if that is the shortest possible chain in the structure. I could have had a 6-carbon chain. I could have had a 5-carbon chain. But my parent was 4 carbons because that was the longest carbon chain that included my highest priority groups. All right, what about the next one? The parent chain and the suffix.
It's from the oxygen substitute to
Good.
propanol.
Propanol. Now, I will say we have to clarify this one differently. I think that I meant to wait to talk about locant sets, but we need to describe that the alcohol is not on the first carbon and that it's actually on the second carbon. So we'll have a locant, but this tells us our root and suffix. Again, we'll come back and we'll talk about how to get that 2 in there. Now, what about the next one? Jacob? Propane diol. That A comes back. I'm sorry, that E comes back at the end of propane so that there's a buffer between the N and the D. All right, the last 2 structures. One has an alkene, one has an alkyne. Both have an alkene and an alkyne. One adds to that and has an alcohol. So the parent chain is going to be the same for both of these. We agree on that? We need to talk about how to get the locants in. I guess I wanted to come back to that because we didn't talk about the locant set. So ignoring how to describe where the locants are, we're just going to say that these are both a 5-carbon chain. And so for the first one, we get this pentene-ine. We're going to have to come back and modify this. It's not perfect. And for the other one, we get penteninol. Yeah. Now, when you guys leave after learning nomenclature and you start looking at ingredients in your food and ingredients in your medication, you're going to start to see these weird little sounding things, and you're going to see why they sound so weird. Penteninol sounds like a medication, to be honest. Like, oh, I'm on penteninol for my bad leg. I don't know. All right, let's flip it over, and let's talk about the next part of our name, which is arguably, usually, the biggest part of the name. This is the suffix spot. By the way, anybody need one that I didn't get one to yet? You want one? Our substituents make up most of a molecule usually. So in these examples that I've given, I wanted to give pretty much all of the substituents you are ever going to come across. And I also wanted to organize them in a specific way. So I want you guys to see if you can figure out what is the organization of these groups. If we have a bromine substituent, we call it bromo. A chlorine substituent, chloro. A 2-carbon substituent, ethyl. Iodo. The ethyl is one I really want to hit on. 2 carbons, eth, not a parent chain, a substituent, a group. So we give it the YL suffix, kind of like alkyl, ethyl. That YL tells you it's a suffix, a substituent group. What functional group do I have here? Do you know? It's an oxygen with carbon on ether. It's a carbon, an oxygen with carbon on ether side. So this is an ether group. The way that we name ether groups is we describe the carbon chain coming off of it and then label it as oxy. It's an alkoxy group. Remember what that ALK tells us? Carbons. Specifically, what type of alkyl group do I have on this alkoxy? A 1-carbon chain. So we'll give it the root. Meth, 1 carbon. Not describing its functionality, just describing the carbon length. So this specifically is a methoxy group. It's an ether. So I need to describe what is the carbon chain, and I need to describe that it's connected by an oxygen.
So the meth substitutes. Meth is just a more specific version of alk.
It could be, yes. Meth is the specific example here of the alkoxy. Could be an ethoxy group. Could be a tert-butoxy group. But an ether will always be that alk-oxy. Okay, and then this last group gets the suffix, gets the name methyl. I want you to see if you can see how these are arranged and why I've organized them in the way that I did. Gavin.
Can you order that in like order of family from like ether to alkoxy to methoxy? Is that the order it goes?
They are, tell me again.
You said it was an ether and an alkoxy and a methoxy.
Okay, so because it's an ether, we named the ether as a substituent by calling it alkoxy. How else do I know? How do I know there's a halogen? I have bromochloroiodo. How do I know I have an alkyl group? Methyl ethyl propyl. How do I know I have an ether group? I have alkoxy, where the ALK is just reminiscent of alkyl, alkane, alkene, also with an oxygen, bridged by an oxygen. So the generic form is alkoxy. This is not a generic alkoxy. It's not RO. It's a specific alkoxy. It's a one-carbon ether, a one-carbon oxy.
So methoxy is just a more specific version of an
Methoxy, exactly. So alkoxy in parentheses because that's how you name any ether. Methoxy not in parentheses because that's how you name this ether.
If it was a 2-carbon, would it be an ethoxy?
Ethoxy. If it were a 4-carbon connected by a tertiary carbon, tert-butoxy.
Okay. That makes sense.
Good. Now I want you to see if you can figure out why did I organize these substituents in the way that I did. Discuss amongst yourselves what you think is the scheme here for about a minute or two while I draw the next one up. All right, I heard this discussion. What about you guys in the back? You seem like you've got a nice huddle going on. Did you see any trends?
Big photo was a whole lot of nothing.
Elvira, do you want to share your perspective?
I said it's alphabetical,
And why? How did you catch that?
because BCEIMN.
Were you looking for alphabetical order for any reason? Maybe because you did the reading?
I did do the reading.
So if you've done the reading, you know that these names in the end are going to have to be assembled alphabetically.
Yeah.
So I wanted to
Make it straightforward.
hit the ground running.
Yeah.
This is going to be assembled alphabetically as well.
But they could be anywhere, and when you just assemble it, you would assemble it alphabetically.
Correct. So I'm only introducing them to you alphabetically because I want you to be thinking about that. We've got different types of groups. We've got alkyl groups, ether groups, halogen groups, but I mixed them all together to show you the alphabetical order. And why does methoxy come before methyl? O comes before Y. We look at the first point of difference to determine the first alphabetically, right? Just because meth and meth are the same, O and Y are not the same. We look for that first point of difference. All right, now I think on this next one, I did not do them alphabetically. But instead, I'm hitting on some of the longer carbon chains. So first, I want to start up here. This is a propyl chain. But because it's a straight carbon chain, we call it N-propyl. Can you guess what the N stands for? Normal. Yeah, it's just normal 3-carbon chain. 3 carbons coming off of the parent. Can you see those 3 carbons? Can you see the separation from the parent? The ring here is our parent chain. I do not count both a carbon in the ring and a carbon out of the ring, one or the other. Now, if I have a 3-carbon chain, but it's attached at the center carbon, we call it isopropyl. And this is a common name that IUPAC has adopted. The iso prefix doesn't necessarily mean anything. Although I do find that in most iso alkyl groups, it's got this little Y at the end, this little peace sign. Gavin?
So is normal linear?
Normal is linear, yep. Going back to alphabetizing, propyl, N-propyl, is named by P. The N there is descriptive. It's just meant to tell you how the propyl chain is appearing. Isopropyl is its name, so it's alphabetized by I. All right, these next 3 we've already seen, or actually some of these next 4 we've already seen. The first one we have is sec-butyl. Then we have that little Y shape at the end, isobutyl, N-butyl, and tert-butyl. Anything that has a dash in the front, it's really hard for me to show it, but actually the descriptors are italicized. N, sec, and tert are descriptors, so we do not use them to alphabetize. But iso is not a descriptor, it's a common name. So we alphabetize by iso. Not my favorite, but when you have that perspective that tert and sec and N are just describing the butyl chain, you're still going to organize it by butyl.
And there's no dash between iso and butyl, so
That's right.
you can look for the dash.
The dash also is evidence that it's not a part of the name for butyl. It's just describing how the butyl shows up. Good point. All right. In the next molecule, what we have are substituted substituents. Substituents that themselves have substituents coming off of. The first one on the right is fairly simple. It's a methyl group that has a chlorine coming off of it. So we call it a chloromethyl. And we put it in parentheses. Because when we add locants, we're going to describe where is the chloromethyl. And I want to make sure that it doesn't feel like I'm naming a chlorine somewhere and a methyl somewhere else. So substituted substituents go in parentheses. This next one is a little bit more challenging because it's a chloroethyl, and so there are 2 places where that chlorine could be. The chlorine could be on the first carbon off of the parent, or it could be on the second carbon off of the parent. So this will be our first exercise in locants. This chlorine is on the first carbon off of the parent chain, so we name it as 1-chloroethyl, again in parentheses, which would be different than 2-chloroethyl. Okay, I want to take you back to some of these names that we had, because we can actually give systematic substituent names for them. Isopropyl is really just a methyl ethyl chain. It's a 2-carbon chain with a methyl group coming off of it. And of course it's coming off of carbon 1 and not 2, because if the methyl came off of the second carbon chain in ethyl, that's just propyl. Sec-butyl is actually a 3-carbon chain, and it has a 1-methyl group. So this is 1-methyl propyl, as opposed to isobutyl, which is 2-methyl propyl. Notice that these are all going in parentheses because they need to be entirely contained. That whole group is one unit, so we put it in parentheses. And then tert-butyl, how would you name that? It does look like 3 methyl groups, but the longest chain is ethyl, and then the other 2 methyl groups are substituents. So this is dimethyl ethyl. Nice. Right? Do you like tert-butyl more, or do you like calling it dimethyl ethyl? Oh, okay. Well, you're allowed to have your opinions. All right, in the last 2, I want to reiterate some of the multipliers. Like here, we saw that we can use di to indicate that there are 2 methyl groups. We would do the same thing here. The longest parent chain has 2 substituents. So this is a dimethyl butane. The substituent is methyl twice, so we emphasize the redundancy of that group, dimethyl.
2-dimethyl butane.
We'll get back to the locants. It's actually going to be 2,2-dimethyl butane, which is different than 2,3-dimethyl butane. So yeah, just for now, I guess we can say the locant there is dimethyl. And here, a 1-carbon chain, CH2, with 2 chlorine groups, so the substituent is dichloro. These are our substituents. And we use the same multipliers in the same way that we did with our suffixes. All right, on to the lowest locant set. We always want to find the lowest locant set. Do you remember when we said we want to find the longest continuous parent chain, ... What did I have you add after that? Find the longest parent chain for the highest priority functional group. Find the lowest locant set ... for the highest priority functional group. If there's an alcohol, give the alcohol its lowest locant. If there's not an alcohol, but there's an alkene, give the alkene its lowest locant. If there's an alcohol and an alkene, give the alcohol its lowest locant, and if that doesn't matter, then go to the alkene, right? Or if you've already done that, then find the alkene. We just go down the list if we can, so that everything has its lowest locant set. All right, well, I want to start with the lowest possible locant set that we can have, and that's actually in rings. So the first compound that we have is a cyclopropane with a methyl group coming off of it. By the way, how do you feel about abbreviating methyl as Me? We could abbreviate it as CH3. We don't have to show it at all. It could just be a line. But we can use those abbreviations. My work up there is getting so cluttered, but there are other abbreviations like ethyl being abbreviated by ET, propyl, isopropyl. One that you guys will see me use a lot is this tert-butyl group, a lowercase t, capital Bu, indicating that we have a tert-butyl substituent. Without having to draw everything out, we can just abbreviate it as TBU. All right, well, I'm on a ring, and I want to say that the methyl group is on the lowest possible position in the ring. Well, that is anywhere. It doesn't matter. In a ring, if I want to number my carbons to describe a location for everything, I can start anywhere I want. For a mono-substituted ring, I don't even need to say that it's on position 1. Of course it is. So the name for this is methyl cyclopropane. We can assume that locant 1 for a mono-substituted ring. Would it be wrong to say 1-methyl cyclopropane? Not at all. Would it be wrong to say 3-methyl cyclopropane? Yes. 3-methyl cyclopropane is just choosing the highest locant. There are 3 carbons in the ring, and to tell me that the methyl group is on carbon 3, but nothing else is on carbons 1 or 2, that would be the wrong answer. 1-methyl cyclopropane, nothing wrong with that, but you won't see it very often. It's often assumed. Okay, my next structure. This is also kind of a mono-substituted ring, but instead of having something that shows up in the prefix, I'm going to have something that shows up in the suffix. Do I need to describe where in the ring that functional group in the suffix appears? I don't need to. So this becomes cyclopentene. But you could call it cyclopent-1-ene, or you could call it 1-cyclopentene. The locant 1 is describing where the alkene appears, but you will never see that very often. You'll see cyclopentene. Here again, I have a mono-substituted ring.
I just had a question about the cyclopentene, because hearing it on its own,
Feels wrong?
you assume that there's just one double bond and not two double.
Oh, because it's not cyclopentadiene.
Okay,
If there's a redundancy of a functional group, we use a multiplier.
Can you remind me what a substituent is?
Yeah, it's kind of like a constituent, but it's something that branches off of. So it's a substituted group. You don't just have a carbon chain, you've got something that's substituted on there coming off of it. Yeah. How would you name this? Cyclohexanol. Could call it 1-cyclohexanol, could call it cyclohexane 1-ol, but you will see this most often referred to as cyclohexanol.
Question.
Tell me.
If there were 2 OH groups, then you would end up with, but would you need to specify the locants? So you would end up with like 1,2-cyclohexanol?
Yep. As soon, yeah. So this, we assume 1 for a mono-substituted ring.
Yeah.
Key word there is mono.
Okay.
As soon as you have 2 groups, you cannot assume anything.
So what would it be if there was another alcohol?
It would depend. Is the other alcohol on the same carbon? That's 1,1. Is it on adjacent carbons? 1,2, 1,3.
So you just say like 1, 2, if it was next to it.
1,2 cyclohexane diol.
Diol.
because that multiplier tells us we have 2. Are these next two structures rings? Excuse me. So can I use this rule of assuming 1? Okay. No, we can't.
Like 1 dash of chlorobutane.
Good. Now I want to work this out. I have 2 different ways that I can number a linear chain. In a ring, I can start wherever the hell I want, because a ring doesn't have a start or a stop. So if there's only one group, yeah, I'm just going to start where that one group is. But on a chain, I have to start at one end or the other. And I think we saw that sometimes chains have all sorts of ends. I need to start at an end of a chain and move to an end of a chain. So I can number from the left, in which case my locant becomes 1. Or I can number from the right, in which case my locant becomes 4. The lowest locant set tells me I have 1 chlorobutane. Calling it 4-chlorobutane breaks the lowest locant set rule. So the way that some textbooks will phrase this is start numbering from the side of the chain, the side of the linear chain that is closest to the substituent. But we can see that again here. If I number from the left to the right, I get locant 2. If I number from the right to the left, I get locant 3. Good. Good. Now these dashes are used to separate locants from other parts of the name. So we have a locant dash whatever substituent it has, it's describing.
On the big ring that we had up there with a bunch of substituents with dashes like ant and n,
Yeah.
you end up with, I don't know, like 1-N-propyl?
Yes. 1-N-propyl cyclohexane. Yep. All those dashes stick around. So you can tell the difference between these two structures by drawing. One is a primary alkyl halide, one is a secondary alkyl halide. But now you can communicate the difference between them by their names as well. This is the foundation of structural isomerism. And IUPAC does a great job at helping us tell structural isomers apart. Structural isomers, by the way, I don't like this name. They're sometimes called constitutional isomers because they're constituted differently. They are built different, they're connected differently. And IUPAC is really good at helping you identify structural isomers. Okay, so let's look at the next structure where we've got both an alkyl substituent and a halogen substituent. Now I don't have just one locant. Now I really have a locant set. You raising your hand?
Yeah. Would you, I kind of drew that a little bit. Would you, the highest priority would be the halogens, right?
Why?
Or sorry, it would be the alkyl.
Why?
Because that's the number one on our priority list. It's alcohol and then it's alkyl and then alkyl and halo, right?
Right, so alkyl and halo
So lower than, so it would be
equal to each other.
equal.
Right? It wasn't alkyl then halogen. It was alkyl and halogen on the same plane. All right, well, once again, I'm going to number from left to right and right to left, and I'm going to look for the lowest locant set, and I find the lowest locant set is 2,3. 2,3 is a lower locant set than 4,5. Do you see why I'm calling it a set? I have A group at 2 and A group at 3, those are my locants. And these groups are equal priority. So it's not like I'm trying to get methyl a lower group or bromo a lower locant. They're equal priority, so I'm looking at the set as a whole.
Oh, okay. I was gonna ask, like, in a case like that, could you then do alphabetical?
Right.
Okay.
Yep, I think we'll have an example that hits on that. So obviously 2 is lower than 4. This molecule has a 2-methyl and a 3-bromo. That's my lowest locant set. You know what? And this is where I screwed up on here. I don't have a part that talks about assembling the name.
I was gonna say, so like 2-methyl, 3-bromohexane,
Nope.
or switch.
Because we're going to alphabetize the substituents. We're gonna keep the locants with their relative substituent as well. These are great.
2-methylhexane.
Perfect. 3-bromo, 2-methylhexane. Notice how the dashes separate words from locants. Notice how the last substituent bleeds into the parent. These are not separate words. This is actually one word. I believe the longest word in the dictionary is the name of a compound because it's technically all one word.
And then if there would be like one more extra bromo group, then it'd be like 3, 4, 5.
Great. Then we use commas to describe all of the locants. Exactly. Yep. And we've got more examples coming that we're going to go through. So all of these questions you guys are hitting on are the right questions, and we're going to exemplify the answers to those questions. Okay, now my molecule has both alkyl, halo, and alkene. Alkene takes higher priority. So I do not care about the total locant set anymore. I care about getting the alkene its lowest locant. How can I give the alkene its lowest locant? Number from the side of the chain that has the alkene. If I can start at the alkene, absolutely I will. Or if I can start closer to the alkene, absolutely I will. Groups go in alphabetically. So I have I'm just going to list it out. I have a 4-bromo and I have a 5-methyl. So now my name becomes 4-bromo dash 5-methyl. Now I have to describe the locant of the alkene. The alkene is 2 carbons. Correct? That's the definition of an alkene, a carbon-carbon double bond. Which carbons do I name? Do I have to name both? Or can we live with the assumption that if I name one, I am counting through the second?
Wouldn't it make sense to leave it hexene then, that it's implied? Because
No, because that double bond could have been anywhere in that chain. There's a lot of places a carbon-carbon double bond could have happened, and I need to say where in the chain.
methyl hex 1-ene.
There's 2 different ways that we can do it. We can put the locant right before the part of the name that clarifies that functional group. 5-methyl hex 1-ene. Where is the alkene? It's at position 1. This is what IUPAC is pushing for, but a lot of people don't really care. And traditionally, this would have been named as 4-bromo, 5-methyl, 1-hexene. But you can see how the 1 isn't describing the placement of hex. Hex is the parent chain. 1 is describing the position of ene. And what if I have more than just ene in my suffix? What if I have ene, ein, all? What gets to go in front? All of them? But then how do I know which one I'm actually describing? One of them, the first one, gets to go in front, and then all the others just go in right before their descriptive part. Typically, we say, I say, just stick with the top. Put the suffix put the locant where it's describing something.
So then, okay, if you had two double bonds, 1 and 3 times to 4, and then 1 to 1 and 2, would you say 1, 2 ene, or would you say if you had the die?
You still add die.
So you'd say
If you got multiple of a
die
certain group,
ene.
yep.
Okay.
Or like actually 1,3 cyclohexadiene is really common. Cyclohexa 1,3-diene versus cyclohexa 1,4-diene. Yeah, so we'll add multipliers and locants.
Can you explain the methyl hex again on the top?
Yeah, right here.
Yeah.
Well, methyl is one of my substituents. I have a 1-carbon group coming off, and I have a 6-carbon chain. So hex is my parent, my root.
So why wouldn't we put that where we're starting? Like, you said you prefer the top, but wouldn't it make more sense to put on the bottom 1-hexene since we're starting at carbon 1? Or
Where is the alkene? I have a 6-carbon chain. Where is the double bond? The double bond starts at the first carbon. The double bond could have started at the second. The double bond could have started at the third. We are assuming that we're counting through the double bond. That's the requirement. Whatever number you describe the alkene with, that's the first carbon of the alkene. And in this case, that was also the first carbon of the chain. The other way I could have named this molecule, I could have named it 3-bromo, 2-methyl, hex 5-ene. The problem with that name, it does not give the lowest locant to the alkene. It doesn't give the lowest possible locant for the alkene. Right, Gavin?
yeah, it doesn't.
So why would I want the alkene to be at 5 if I can have the alkene start at 1?
Well, I understand that. I'm just wondering why you say we could do methyl hex instead of 1-hexene.
Because 1 is describing the alkene. 1 is not describing the 6-carbon chain.
Isn't 5 just describing the methyl?
Yeah, 5 describes where the methyl is along the hexane, and 1 describes where the alkene is along the hexane.
But you're also saying 5-methyl describes the hex.
No, sorry. Let's see if this helps. Prefix, root, locant, suffix, and what do you see at the very top of this document again, Gavin? Prefix, prefix, root, locant, suffix. Prefix, root, locant, suffix.
So that's the preferred order then, is what you're saying?
Not preferred, necessary,
Oh, so the first one is more correct than the second one?
according to IUPAC.
Okay.
But taking that locant and bringing it in front of the root is common. It is commonly practiced.
Okay, just because it kind of sounds better?
Yeah,
Okay.
looks cleaner. But this is what I would encourage you to do as well.
Okay.
I do want you to be familiar with both, but I think I agree with IUPAC. This is the most descriptive way to do it.
That makes more sense then.
Great. Yeah.
If you use either or, would it be marked correct?
You could use either or, as long as you do it correctly.
Yes.
Yep. Okay, next one. I've got a ring. What's my highest priority functional group? Correct. There is no highest priority functional group. Where should I start numbering in this ring? Yeah, I would say start numbering where a substituent is, and then number in such a way to get the lowest locant set. Maybe, but we're going to talk about the alphabetical order thing. So let me give you a few examples. If I start at chlorine, I could go counterclockwise, and I would get a locant set of 1, 5. If I start at chlorine and I go clockwise, I get a locant set of 1, 2. If I start at methyl and go counterclockwise, I get a locant set of 1, 2. So obviously my lowest locant set is 1, 2. I have two options to get a locant set of 1, 2. So far, we have not seen a tied locant set. If you have a tied locant set and the groups are equal priority, then we say that the tie goes to the first alphabetical. This is either 1-chloro-2-methyl or 2-chloro-1-methyl. Chloro wins out alphabetically. So only for that reason. True or false? Chlorine is a higher priority functional group, which is why it got position 1. False. Chlorine is not a higher priority functional group. It got position 1 because it is first alphabetically. 1-chloro, 2-methyl, cyclopentane. What's the difference between that structure we just named and the next structure? So what are my possible locant sets? Would you guys agree that I could start at chlorine and number clockwise, and I get a locant set of 1, 2, 2? Or I start at the methyls, and I number counterclockwise, and I get a locant set of 1, 1, 2. Ooh. Don't just go alphabetical.
No, this set gives it its lower locants and more lower locants at first alphabet.
Always find the lowest locant set. The lowest locant set here is at the first point of difference. You guys recognized earlier that methyl and methoxy are different at the O and Y. Here, my locant sets both start with 1, but my second number is the first point of difference. So instead of having 1-chloro and 2,2-dimethyl, and I do want to write that out to clarify it for you, both of the methyls are at position 2. That's significant. It's not 1 at 2 and 1 at 3 or 1 at 2 and 1 at 4. So I'll say both locants and I'll say dimethyl. Now instead we have 2-chloro and 1,1-dimethyl. Yeah. Now, when I name this, I know that C and D, I mean, still the chlorine is before, C comes before D, C comes before M. But when I name this alphabetically, am I alphabetizing M or D for dimethyl?
You're prioritizing the M and the C because di is just the multiplier.
Di is just the multiplier, it's not the group itself. So chlorine and methyl are still how I alphabetize this. The only time that that is not true is when you have a substituent, like a substituted substituent. For instance, we had dimethyl ethyl before as our way of saying tert butyl, and that gets alphabetized by D. The first letter in a parentheses is used to alphabetize, but otherwise, otherwise multipliers are not used. In parentheses, use the first letter. All right, so this all comes together to give us 2-chloro, 1,1-dimethyl, cyclopentane. Now, I get a lot of pushback, as if I wrote these rules, from people that say, why do I have to say both locant positions and the multiplier? to be redundant. That is the goal. Make it clear without a shadow of a doubt where your structure lies. If it seems silly because, duh, of course there's 2 methyls, I gave 2 locants, good, then they can't possibly get it wrong, right?
It always goes alphabetical. You wouldn't put the one locant first.
We're not naming it by the locant. We're naming it alphabetically. So those 2 molecules are very similar to each other. One of them is 1-chloro-2-methyl, and the other is 2-chloro-1,1-dimethyl. The locant number does not impact where things go. Okay, so here's my tips to you if you're naming a molecule. First, find the parent chain. Then, find the lowest locant set. Then, assemble the name, alphabetize. And when you're finding that lowest locant set, I want you to do kind of like what you're doing over there, listing them, and then also, oh, I should do this, specifying it. Find your substituents, group them with your locants, so that all you have, just assemble all these pieces, so that all you have to do is put them in line. Okay, we have a couple of other molecules left. So on the bottom, what name should I give to this compound? Feel free to think about it. Look it over. Where are you going to start?
I'll take a shot. This might be off.
Let me hear it.
3-methyl cyclo hex-1-ene.
All right, my guess is that you named it this way then.
Yeah.
And with our alkenes, we have to count through them.
So you have to go through
4-methyl
So
cyclohexene
4-methyl
1.
cyclohex-1-ene.
So we're going to shift it just back, but go in the same direction.
Yeah.
Great. Now, what is my highest priority functional group?
The alkene.
The alkene, which is why you started at the alkene. If I'm in a ring, is there any particular place I need to start? No. So I'm going to start at the highest priority group. Since I know I'm going to start at the alkene, do I have to say that the alkene is at position 1? That's kind of our rule, is I have to start at the alkene. So not wrong to say 4-methyl 1-cyclohexene, 4-methyl cyclohex-1-ene, but you will also see this as 4-methyl cyclohexene. That's a lot of E's, all back to back. So this is what you would likely see, but you are never incorrect to say 1-cyclohexene or to say cyclohex-1-ene.
So because it's a ring, we can get away with the cyclohexene. But
Because it's a ring,
that has to be the hex-1-ene.
even though this one started at 1.
Yeah.
I had to clarify that the alkene did start at 1. But because it's a ring, I can start from pretty much anywhere. I have to start in a specific spot here, so I have to use locants in my chains. I can start from anywhere I really want in a ring, so I don't always need them. Usually only for that highest priority group.
What if the cyclohexene has multiple double bonds?
Right, well then you have to specify where both of the double bonds are. Yep. So you could say like 1, and then if I had another start at 3, or 1 and then another start at 4, but I'd have to say 1,3-diene, 1,4-diene. Because now I have more than one group, I can't, it's not just the one priority. For the next one, my highest priority. Michael, you want to name it?
Yeah, the highest priority is the alcohol.
And so I'm going to start at the alcohol. And I can go clockwise or counterclockwise. Why?
Is the next one, right?
So now that I've started at the alcohol, it has its lowest locant set. I now have different locant sets that I could give to my other groups. So I'm going to find my next highest priority and make sure that it gets its lowest locant set. I've already satisfied alcohol, but now my alkene could go one or the other way. So now I'm going to aim to satisfy my alkene. Okay, anybody want to piece together the full name?
Is it 6-iodo-cyclohex-2-ene-1-ol?
Yeah. Did you say 1-ene?
No, 2-ene-1-ol.
Good. So I would, once again, assume the alcohol at position 1. Because of course it is. It's the highest group. So you're going to start at the alcohol. And then I like to put that 2 in front of the ene, but you can call this 6-iodo-2-cyclohexene-ol. Do you see how the 2 can only describe whatever the first thing is after the root?
If you have multiple, you're in trouble.
You're in trouble, but really you can just put your locants inside.
But you wouldn't be able to do it without putting your locants inside if you had multiple alkenes.
Correct. Or we can call this 6-iodo-cyclohex-2-ene-1-ol, as Michael gave us. Complicated little bugger. Yeah?
But all 3 are correct.
All 3 are good. 2 of them rely on the assumption of the highest priority functional group and just differ on this, like, should the locant go right before what it describes, or can it come before the root as well?
And naming the alcohol will always be at the end.
That's, well, okay, no. We can name an alcohol as a prefix, and it's named similar to an ether, but instead of alkoxy, because it's not an alkane group, it's a hydroxy because it's a hydrogen group. Hydroxy is the substituent name. But for our class, this is the highest priority functional group. So it always has a spot in the suffix. If there's a higher priority, like an aldehyde or a ketone or carboxylic acid, the alcohol has to be named as a substituent, and there it's just called hydroxy.
But we're not there yet.
We won't do it, yeah. OChem 2. All right, fun stuff, right? If we go back and look at some of the molecules we skipped over at the beginning, like when we were doing suffix stoppers, and multipliers, now we know that we should really call that first molecule 2-ethyl pent-1-ene. We didn't describe that 2-carbon chain that came off of the pentene, and we didn't clarify that the alkene was at position 1, which is different than if the alkene is at position 2. The second molecule became 2-N-propyl butadiene. You could call this 1,3-butadiene, but there's not really any other butadiene. There's just not a lot of carbons to have 2 alkenes in there.
Where's the N from again?
It's a normal chain. It's a straight chain. It's not an isopropyl chain. Now we know that we should call it 2-propanol, or better, propan-2-ol. And we know that we should call it propane-1,2-diol. Those are our next 2 molecules. Notice how that propane got its E back.
Why is the next one?
No.
Wait, which one are we looking at? Are we looking at the
Yeah, which one?
It's the alcohol.
The diol
one with the two alcohols on it, right?
should be 1, 2. If I start from the right, I have one alcohol at carbon 1, one alcohol at carbon 2. And what am I misunderstanding? How would I get 1, 3 anyways?
Oh, yeah.
Oh, okay, okay. Good. I mean, I could see 1, 2 or 2, 3, but 2, 3 would be a higher locant set. Okay, what about for the alkene and the alkyne? I can either start from the alkene or I can start from the alkyne. Why would I choose one or the other? They're tied priorities, right? Alkene and alkyne are tied, and they have the same locant set here. Either the alkene starts at 1 or the alkyne starts at 1. Tie goes first alphabetically. So only because of the alkene, we'll start from the alkene. And this gives us pent 1-ene 4-ine. You agree the alkyne starts at 4? Now for the next one, the alcohol is the highest priority. But the alcohol is going to end up on carbon 3 no matter what. If I start from the alkene, the alcohol's on carbon 3. If I start from the alkyne, the alcohol's on carbon 3. So the alcohol has its lowest locant. So still a tie, alphabetical, between alkene and alkyne. And I get pent 1-ene 4-ine 3-ol. Now, remember what we were talking about before, what happens when I've got all those locants in the suffix? The first one can come out. 1 pentene, that was someone else's computer, right? Not mine. Oh, thank goodness. 1 pentene 4-ine 3-ol. Only the first thing could come out. All of the other suffixes have to keep their locants next to them, which is again why I think this is a better system of naming.
So that one is fine, the top one.
Yep.
If the alcohol is closer to the alkene, would you have to start from the alkene?
If the alcohol is closer to one side or the other,
You would start.
disregard the alkene and the alkyne and make sure the alcohol has its lowest locant. And then the alkene and alkyne just get whatever they get based on the alcohol getting its lowest locant.
How come we started with the locants on all the other ones and then these we start with locant?
Tell me again.
On all the other compounds we start with the locant?
Oh.
But on any of these we didn't?
These don't have substituents.
Okay.
Everything is built into that 5-carbon chain. Well, here we did 2-ethyl, that had a substituent. 2-ethyl pent 1-ene. But I think you're noticing that propane 1,2-diol doesn't have any substituents coming off. It doesn't have alkyl, it doesn't have halogens. So there's no prefix to that molecule. Yeah, good point. Okay, we'll finish this worksheet tomorrow just briefly with stereoisomers, which is going to move us from regiochemistry into stereochemistry. And the rest of this unit is all on stereochemistry. Have a good day. See you guys tomorrow.
So all this is just regiochemistry.
All regio. No, I mean, nomenclature really is mostly regio. But we're going to see tomorrow how we can also infer stereochemistry in the name. So we can use the name for both regio and stereochemistry.
Do you want to drive today?